Thank you very much for having me. It was lovely to be invited to show what I've been up to. So this is some of the work that I was doing as a final part of my PhD. So we're kind of finishing it off now. Ready for doing further tests post PhD. So I'm going to be talking about Afar, but before I start with that, I'd like to thank essentially a whole load of people that have been involved in this project. It's not been a small feat. It's been a big project. So thank you to everyone that's involved. There were probably tons of people, but that's some of them there from a range of institutions. So the key thing I want everyone to kind of my key message for today's kind of talk, or from my talk at least, is that I think our research has shown that, and I will talk about how we found that, is to fully understand our mantle upwellings around the world. We kind of need to use an integrated approach, so not just geochemistry, not just geophysics, but try to communicate between the fields and match all this information together to fully optimize what we can see through both kind of fields and other fields as well, because they all have their downfalls and their benefits. So using them together kind of hopefully will benefit those and maximize the output we can see in our understanding. So Ian kind of talked a little bit about the East African Rift. So we're going to move slightly further north in the rift for this talk to an area called Afar, known as also the Afar Triangle. So we can see the main Ethiopian rift coming from the bottom right of the diagram. No, bottom left. Might help if I knew my left and rights. So from the bottom left here, and then we're looking into this Gulf of Aden, Red Sea, main Ethiopian rift triple junction. So the triple junction is around where my mouse is currently, and it's comprised of the three rifts itself. And it's a really unique place because it is a triple junction that is actually subaerial at the time. So we often have these kind of triple junctions, but they're often quite underwater by the time you see the extension to what we see now. So this is quite a unique opportunity, and it's thought to be underlain, as Ian kind of suggested, by mantle upwellings, and our volcanism in the area has been kind of prevalent since about 30 million years ago. Okay, it's now concentrated on these axial rifts, which are shown as this dark red kind of pattern all around. And this is where, since about 500,000 years ago, that's where our volcanism has been concentrated. So we're going to be focusing on these for this talk. But before we kind of carry on, what I think we need to be aware of is the progression of our understanding of mantle upwellings within Afar since kind of our research began. So please be aware, this is a summary. There has been like hundreds, if not thousands, of amazing studies on the region. I couldn't show them all, so this is just a quick talk through. So don't be alarmed if your paper or someone you know isn't on here. It's not a dig at all. So we started in about the late 1800s. Gregory went out and found the East African Rift. So that's kind of where researchers started. And since then, in about 1970s, Schilling went out and first proposed this idea of mantle plume. He kind of saw these high radiogenic or unique radiogenic signatures. And this was kind of further backed up by Vidal and that paper. And they considered this to be a high mu source, the mantle source or the melt. And a high mu source is essentially a high uranium to lead ratio, which is associated with potential recycling of oceanic crust and then further being upwelled after depletion in the fluid mobile lead. So this kind of high mu signature indicates there might have been some deep upwelling from a past subduction event. In 1992, Schilling then put a paper out, again saying whether it was a high mu source, but doing quite a lot of research looking into these variations across the region. So he focused on the Gulf of Aden and got some really good data across the rift, and then supplemented that with some of the data that was around from the Red Sea Rift and the Ethiopian Rift, trying to look at how this variation happens radially from what was thought to be the plume center at Lake Ebbe, where I had my little mouse at the start of the triple junction. Other work has been done since, and there's been some really good papers showing with geophysics this time rather than geochemistry, that there was a single plume, and this was done through mathematical modeling with some geology knowledge, so showing how the melt thickness kind of varies with distance, and again how if the singular plume is likely expanded over time. Again, we then had a more purely geophysical study by Ritzema, and these were the first people to kind of view this super plume that Ian showed in his images as well. And you can kind of see this rising from the base of South Africa, from the core mantle boundary up, and then this kind of hotter, more melt-prone area around Afar, and that kind of Ethiopian region. But then we had some other papers that come up that kind of debate whether there is actually a plume present. So in 2012, there was a paper by Reicher et al., and they argued that the decompression melting might have been dominant rather than a mantle plume or upwelling. So there's been this kind of back and forth debate of different methods and different findings. Since then, we've had a few more geochemistry studies. Rooney's done some very, very large studies, published many papers, and kind of a real good review on the whole region. And they suggested that there was 5 different kind of melt sources, and some of these were linked to a plume and some were not. So there's this kind of debate of how much and how wide the influence of the plume is and over time. Finally, we then had some geophysics papers in the last few years, and these have been really interesting, and putting out a completely different side of things, of rather than a singular plume, maybe as resolution of these geophysical techniques has improved, maybe there's actually some plumelets or smaller scale multiple plumes within the region. So Siviera et al. Kind of have been suggesting this, and Emma Chambers' models showing some melting in the region kind of shows this lateral or spatial variability in melting across the Afar Triangle. So there's been some progression of these kind of concepts of whether there's a single plume, a plume at all, even whether there's multiple plumes of a smaller scale within the region throughout time. But what we'll see, other than a couple of studies in the region, they tend to use one method, either geochemistry or geophysics, and rarely are they trying to integrate the two. And so that's kind of where our study kind of comes in. So I aim to kind of combine the two because I kind of saw this disparity, and I was quite intrigued to see why that was the case and how we could mitigate that. So what we've kind of done is we've identified multiple indicators, both geophysics and geochemistry, of which can be used to identify mantle upwelling. So some of this is seismic velocities, so shear wave velocities. Some of this are isotopic data, the MOHO depth, and other things such as like trace element ratios that can indicate a higher degree of melting or such. And so that's just a flavor of some of the things. And we've actually supplemented this with over 100 new data points and sample analyses of the geochemistry. Because that was one of the big kind of problems in the past, was that there wasn't a high enough sample density to really understand the region in a whole. Because the key thing for us to be able to combine both geophysics and geochemistry is they have to be from the same age period. We can't compare things. If you're imaging now, then you're imaging a snapshot of the mantle at this present moment. Where if you're analysing samples that were erupted 30 million years ago, you're going to get a very different signature if that mantle has evolved. And so we have focused on our study of using eruptions that have happened at volcanoes within these axial segments that I mentioned at the start. And these have all been active within the Holocene. Okay, so we're really focusing on our recent volcanism. Okay, so it's going to allow us to indicate our new kind of upper mantle signatures, and hopefully you can see that we have quite a large sample density. So the darker, more purple the hexagons are here, this hex plot indicates a higher amount of samples, but we've got a pretty good spread across a lot of these kind of images, a lot of these rifts. And this is a combination of our new data, over 100 new data points, as well as previously published data in the region. So we're combining all the information we can to have this best output. So
roughly 10 minutes now.
Okay, perfect. So what we kind of have done is we defined our problem that we can kind of image this plume using the maximum resolution, trying to use our geochemistry to optimize this lack of geophysical small scale resolution. We decided which variables we have, so we've identified 12 main variables, and we filtered our previously published data sets to make sure that we could use all the variables available. We then sampled based on these gaps in our region, our new over 100 new samples analysis, and then we've now applied some statistical analyses of this data set. Okay, so that's what we're going to kind of go through there, show some of our preliminary findings of that, and explain what we're going to do now. So to be able to do our statistical analysis, which allowed us to combine these two methods, we had to come up with some models. So we came up with 5 different models, each having 2 variables. Okay, so hopefully I can give you a brief outlook of these models. So we started with model 1, which is a C1C, is known as, just for our notation. And this indicated a single upwelling centered at Lake Ebet, and it was spreading equally across all 3 rifts. Now, for all of these, we allowed a linear or a spline model, assuming that the plume signature or the upwelling signature would decay with distance from that plume, from that upwelling center. Okay, so the spline allows for any variations or heterogeneities within the upwelling, where a linear assumes it's constant and it just degrades with distance. Okay, so C1C was, as I said, the single plume equal across all rifts. We then used Caviero's kind of model of having some plumelets. So we tested 3 small plumes based on her study with their locations, as you can see here. And again, they would be equal across all 3 rifts. We then had a single plume that would spread out differently across each rift, depending on that rift's scenario. Then we had, again, similar, allowing different rifts to behave independently, but having 3 similar composition plumes. So C3D allows the plumes all having the same starting composition at any point, but they would spread differently amongst the rifts. So assuming that they would have a similar parent body from that melt. And then the final one had the most independents or variables that could change. And this would allow for all 3 plumes or plumelets to behave independently of each other. So all have their own composition, but they would also spread differently across each rift. So we kind of tried to test as many different models that we'd kind of come up with out there, and to see whether they would kind of work. So what we did was we had our data. We would plot different indicators with distance, our 12 indicators, and we would see whether these models predicted this data very well. And what we kind of come up with is plots like this. So this is 2 of our variables we picked. So this is delta lead and shear velocity. And you can see our data points across distance. Okay, and these are the lines that a model would fit. Okay, so this was from the C1D model, and we could see whether essentially we'd split our data up into 80%, 10%, 10%. 80 allowed our model to be fitted, especially with our splines. 10% would allow the roughness, and then the final 10% was to test that model. Okay, so how good was it predicting our data points? Okay, and our initial findings are as such. So as I just described, we then use our test data. So how good is that model at predicting where our data would be? So by doing that, we get a mean standardized root mean squared error of prediction. And all that means is predicting the distance from that line to our data points. Okay. And so what we want is a prediction of 1 means it was a terrible prediction. Okay, there was a lot of error in it. And a prediction of 0 is our perfect fit. Okay, and so what you can see from this is our models kind of predict that C1D is a single plume that's spreading heterogeneously across each rift is our best fitting model. Okay, but it's not just the linear model, it's got to allow for some heterogeneities within the plume itself. So this kind of spline model. Okay, so we see that that's our winning model and what it indicates. And I just want to note that we have repeated this test when we exclude samples that appear to have significant crustal contamination, because that can cause problems with some geochemistry. So any of those samples that seemed like it had significant crustal contamination, and we use serum lead ratio as an indicator of that, we took those out and we reran the model, and it came up with the same winning model. It was very, very similar to its prediction. So that's kind of what we've done so far. Our further work is we're going to kind of build on this and do even more statistical tests. So we're going to investigate and see if we can characterize these geochemical heterogeneities that this C1D spline model indicates using principal component analysis and cluster analysis. So that's kind of where we're going next. But hopefully you can see that we're kind of trying to integrate these quite well to really indicate this picture. So to summarize, obviously everyone knows that kind of the nature of the mantle being Afar is kind of long debated and there's a lot of studies on it, but our models combining both geophysics and geochemistry using maths and statistics signify there might be a heterogeneous upwelling beneath Afar. But we really need this integrated approach to keep moving forward in the field, in my opinion. Thank you very much. Any questions?
Thank you, Emma. That was great. I really like your methodological approach. It's nice and compelling.
Thank you.
Does anybody have any questions? Either put your hand up or you can put something in the chat. Got a wee bit of time.
Hopefully it wasn't too quick. I was trying to stick to time.
No, that was great. Kathy, you can ask first. Kathy Whaler.
Okay, I think Sasha had his hand up first.
It's okay, but he's a co-convener, so he gets back of the queue.
I was just going to ask you, Emma, how you factor in the number of independent variables, because obviously the more variables you have, the better the fit you expect. Although from my simple reading of what you've done, it wasn't the model with the most variables that provided the best fit. So I was just interested in how that part of it worked.
Yeah, so it was exactly that. We were kind of expecting the model with the most variables, so that's that final model that was on the right hand side, to have the best fit, and then we would kind of go from there and then try and refine it. But the fact that it didn't kind of struck us straight away with that maybe that is quite compelling that that's actually not the case. And so the way that we kind of limit these, obviously we can't refine how many variables because naturally the models are going to have different amounts, but we kind of try to limit the variables themselves by standardizing the 12 variables we put in to make sure that then the sizes of those at least are not having any weightings. And we tried to have an equal amount of geochemistry and geophysical variables so that we weren't overly weighting one side or the other in terms of that variability. But we can't, in the models themselves, the 5 different models, we couldn't account for that varying amounts of independence in their kind of features, because that's just kind of how they are in their own rights, I guess.
Okay, so it's when you come to the interpretation stage that you build that in. Thanks very much.
Thank you.
And a final question from Sasha.
Thanks. Very nice talk, Emma. Could you go to the diagram where you show the fit of all the different models, please?
Oh, yeah. 1 second. Oh, there we go. This one.
Yeah, this one. I was surprised to see C1C, the one on the left, being worse, and C1D, the one that's kind of similar because you still have one plume, being the best. Yeah. And I wanted to hear your opinion. What makes this difference, and whether it is so? One thing that came to my mind is maybe that the lithosphere thickness in the Red Sea and the Gulf of Aden, because they are more evolved, they have a big imprint on this data points that you see here. And as a side question, whether it would be possible to factor that in, that you maybe have 3 arms in C1D that have a different impact on these fits.
Yeah, so it's exactly that. So with the model, we C1C, because we're assuming that all the rifts have equal weighting or equal distribution, they fit one line. So there is more variation available and more independence in that C1D. So I think that's part of it. But I think from an actual geological point of view, why that's fitting better is as you said, they have very different properties on each of the rifts. And giving it that amount of freedom allows for those properties to have influenced the mantle as we probably would expect them to. So these different rates of rifting, the different lithospheric thicknesses likely impact the amount that the plume is spread out over time. And so I think that's what we're seeing here, is that kind of shown in the diagram almost, that different amount of reflection of how it's spreading is linked to the actual rifting and the dynamic processes associated with the rifting. Does that kind of answer your question?
Yeah, very well.
So we're going to kind of try and do some further statistical testing is kind of what we're going to then exploit to see if we can understand that even further, to see why we're getting that winning model being that kind of pattern.
Good. Thanks.
Cheers.